This video is the continuation of my last video in how to find the state or the phase of a substance using tables in the back of your textbook. So if you haven't watched my first video, I recommend that you do. But anyways, let's go ahead and get started with part 2. What state is water in at a temperature of 282 degrees Celsius and a specific volume of 0.01 meters cubed per kilogram? Find its specific internal energy value. So, highlight important parts. We're looking at water, temperature, and specific volume. I'm going to rewrite it because if you pick the wrong tables, everything is wrong. Alrighty. Now, we're looking for the internal energy and the state. So we have water. What we will always do first when we're given two properties like temperature or specific volume, we're going to look up temperature at 282 degrees Celsius in table 5.1 because that's the saturated water tables according to temperature. So let's go ahead and do table 5.1. And we're going to go ahead and compare the specific volume values. Already in temperature of 282. Here we go. Temperature 282. And this is where we run into problems. So we have temperature at 280 and 285. But we don't have values at 282. So that means we're going to have to do linear interpolation. However, we're going to need linear interpolation to figure out the specific internal energy value, but we don't really have to do it in order to figure out what the phase is, because we can just kind of eyeball it. So our given specific volume is 0.01 meters cubed per kilogram. And I see here that the saturated vapor volumes for these guys are at 0.03 and our specific volume for saturated, I picked the wrong ones. These guys, 0.03 and 0.02. So really close to 0.03. And we have 0.01. And the saturated liquid volume are those guys right there, 0.001. So we know that at 282, our values are going to be really close to those. That means that our specific volume of 0.01, the one that is given to us, lands between the saturated liquid and the saturated vapor values. So if it lands in between those two numbers, that means that it's a saturated mixture. So I'm going to go ahead and write that it's a saturated mixture, but also take a note of these these 6 values. So 280, the 285, and these guys right here. Probably also this guy. So I'm going to take a note of these because we're going to need them. And you'll see why. So we notice that our V given is in between the saturated liquid value and the saturated vapor value, which means that it's a saturated mixture. Right, because it's 0.01 and our saturated vapor volume value was 0.03, and our specific liquid value or specific volume of saturated liquid was like 0.001. So it lands in between both of them. That means that it's a saturated mixture. So if it's going to be somewhere under the dome, right? But in order to figure out where exactly it's going to be for a saturated mixture, we need quality. All right, if you have a saturated mixture, if saturated mixture, then we need quality. The formula for quality is this one right here. Alrighty. And we need quality in order to find U. Alrighty. We have V given. V given is going to be 0.01 meters cubed per kilogram. However, we need to find saturated liquid and the saturated liquid gas or liquid vapor values. And we're going to need a lot of linear interpolation, so bear with me. So I'm going to go ahead and set it up. So at temperature of 280, we had the specific volume of saturated liquid to be 0.001332. Then we have 282. This is the guy we're trying to find. And at 285, we had the specific volume of a saturated liquid to be 0.001348. Alrighty. In order to figure out this guy right here, we're going to need the following. We're going to need the next formula. So let's say this is how I organized it. So again, we're looking for Y2, and each number corresponds with like where it is in the column. So like 280 is X1, 0.001332 is Y1, and they correspond. Okay. And the formula to figure out Y2 is X2 minus X1 times Y3 minus Y1 divided by X3 minus X1 plus Y1. I'm not going to plug it in because this video is way too long already. So when you plug in your X2, your X1, Y3, Y1, and stuff like that, you get that your Y2, or your specific volume of saturated liquid, is 0.001334. Go ahead and plug it in, use a calculator, figure it out. You can do it. So we have saturated liquid. Now we need the saturated liquid vapor value. Again, same exact thing. Temperature, but now we're going to use the liquid vapor values. We took a note of them earlier. If you don't remember them, go back and look at them in your textbook or rewind this video so you can compare and see where I got these values from. They're from the table. I underlined them in red. At 280, the value was 0.02884. We're trying to figure out that guy. And at 285, the value was 0.02642. Again, this is X1, Y1, X2, Y2, X3, Y3. We're looking for Y2. Formula is here on the top. I'm not going to rewrite it. And when you plug it into your formula and into your calculator, I recommend to code it into your calculator just so you don't waste so much time. But it's up to you. Or if you're allowed to use Excel or your laptop, there are online calculators where you can look this up. Liquid vapor will be 0.027872. Again, I got it based off of that equation right there. Just plug in your X2, your X1, Y3, Y1, and your X3, and you should get the same exact values as I have. Alright, finally, I have all the stuff I need to figure out quality. Finally. So, quality is equal to my specific volume given minus the saturated liquid volume, which is 0.001338 divided by the liquid vapor, which is 0.027872. Plug it into your calculator and you get that the quality is 0.3108. Perfect. And now we need to figure out our internal energy. And if you remember from our other example, our internal energy equation is the following. It's this guy right here. So we have quality, great. However, we need to find saturated vapor and the saturated liquid values. And we do so again with linear interpolation. Just a bunch of it, but it's good practice. The temperature is still the same, 280, 282, and 285. And now instead we're going to use U liquid. We're going to go to our table, the 5.11. 5.11? No, it wasn't 5.11. What was it? Was it 5.1? What are we looking at right now? 5.1. Hold up. Let me remind myself what I'm even looking at. Just kidding. 5.1. There we go. Found it. Now we're looking at our internal energy values. So I'm probably gonna be using this guy right here, this guy right there, and this guy right there, and that guy right there, in order to plug in to my formula and figure out what the specific internal energy is at 282 using the quality I have already found. So my saturated liquid values are the following. If you don't remember them, go ahead and look them up in your textbook or just rewind and see where I got these numbers from. We're looking for Y2. Plug them into the formula I gave you earlier, and you should get that Y2, or your internal energy of saturated liquid, is 1,237.65. Perfect. We have our saturated liquid. Now we need saturated vapor. So same thing again, but now for vapor. We have 280, 282, 285. These are their values. Rewind to look at them if you don't remember. We're looking for Y2. Plug it into this formula right there. And you should get that Y2, or internal energy of the saturated vapor, is 2,584.206. Great. Now we plug it into our formula. So U is equal to the quality, which was 0.3108. Our quality, yes. Times 2,584.206, which was our internal energy for the saturated vapor, plus 1 minus the quality, times the saturated liquid value, which was 1,237.65. And after plugging it into your calculator, you get that U is equal to 1,656.1596 kilojoules per kilogram. Again, those units come from your table. They're in the top. If you want to plot it, find P the same way you know that it's a saturated mixture, so it has to be in here somewhere, and it's 0.3, so it'll be more towards this side, towards the left of your dome. But anyways, that's it for problem 4. Let's go ahead and do our last problem. Question 5 says, what state is water in at a pressure of 140 kilopascals and a temperature of 320 degrees Celsius? So our substance is water. The pressure given is 140 kilopascals. And the temperature given is 320 degrees Celsius. We need to find the state or the phase and the specific internal energy value. Alrighty, we're going to figure out the phase by looking it up. We're going to look up pressure at 140 kilopascals in table 5.2. Table 5.2, properties of saturated water, pressure table. And we see here that it's not given. Pressure at 140 is not given. Instead, we have pressure at 125 and 150. However, we have the temperature, the saturated temperature at 125 is 105.99 degrees Celsius. And the saturated temperature at the pressure of 150 kilopascals is 111.37 degrees Celsius. So we can sort of ballpark it. We can figure out the exact value by linear interpolation. However, I am lazy and I'm not going to do that. So I'm going to go ahead and ballpark it that at a pressure of 140, the saturated temperature is, I'm going to say 109 degrees Celsius, because that's fine. It's close enough, I think, hopefully. 109. So the T given, which is 320, is much greater than the temperature saturated, or the saturated temperature at 140 kilopascals. And with that information alone, we can figure out, we know if it's superheated or if it's a compressed liquid. And I'll show you why. So at pressure of 140 kilopascals, this is going to be the temperature trend line. But at our T saturated, which we said was 109 degrees Celsius. In that right there, our pressure or saturated pressure at 109 degrees Celsius is 140. It's 140 kilopascals. Great. However, our temperature is not 109. It's greater than that. It's 320. So I'm going to go ahead and draw the trend line for that. Temperature of 320 degrees Celsius. Great. But we know that the pressure that we need and our pressure given is 140. So if I were to continue to draw this trend line for it to hit the 140 mark, we see that it will land right there, right? Because that's where 140 kilopascals lands, which is our P given, and our T given, which is 320 degrees Celsius. So and our point is to the right of the dome, so that means it's going to be superheated. Again, it's just a lot of practice for you to be able to see it. And also at the end, I'll give you a little cheat sheet so that you don't always have to draw it. You still need to be able to draw it, but sometimes we need to move fast, and it's easier to just have a little cheat sheet next to you. Alright, it's superheated. So we're going to look up, we need to find the internal energy values, and in order to do that, we need tables, but it's not saturated, so we're not going to look at saturated liquid or saturated vapor tables. We're going to look at superheated steam or superheated vapor tables. So we're going to look up temperature at 320 degrees Celsius at pressure of 140 kilopascals in table 5.3, because that's our superheated steam, superheated vapor for water. So table 5.3. Great. And I'm going to look up temperature at 320 degrees Celsius and our pressure at 140 kilopascals. So this is 10 kilopascals, 50 kilopascals, 100, and 200. Alrighty, they don't give us 140. So we're going to need to interpolate. Now we need to figure out if it's going to be linear or if it's going to be double interpolation. We need the temperature given at 320. However, we have temperature at 300 and temperature at 400. So that means we're going to do double interpolation to figure out our value for our internal energy, which is our U. So let's go ahead and pick up the values that we need. So we're going to need this guy right here. This is our internal. We're going to need this value. We're going to need that value. And we're going to need internal energy, the second column. So we're going to need this guy, that guy, as well as our pressures and the corresponding temperatures. So alrighty, make sure you memorize those, write those down. We're going to need them for double interpolation. Alright, I like setting up my double interpolation with this table right here. Again, we are not given, no, we are given. We cannot find T equals 320, and we also P equals 140. So double interpolation. Alrighty, I like setting it up like this table is right here. So our Y1, Y, and Y2 are going to be my temperatures. So we have temperature at 300. We're looking for it at 320, and we're also given our 400. So this is my Y1, that one right there. This is my Y, and that's my Y2. It corresponds to the table on the left. And it's important because you're going to plug it into this long equation right there, or you can code it, or you can look it up online if you're allowed to use your computer or your phone during your exam. And our pressures at 100, we're looking for it at 140, and we also have values for pressure at 200 kilopascals. We write down their corresponding values for internal energy. Great. And now we're looking for P. Right? You plug in those values to this really long equation, or again, look it up online. I would recommend to just code it or download a program or just look it up online, and you'll get, after plugging in, this would be your Q11, this is your Q12, this is your Q21, and that's your Q22. And after plugging everything in, you'll get that your P value is equal to 2841.21. So your internal energy, or your specific internal energy, is 2841.21 kilojoules per kilogram. And that's how you solve that one. And that's it. those are the 5 examples I had. I'm going to go ahead and show you a little cheat sheet I made for myself when you're trying to figure out the state of the substance. So if you're given P and T, you can either look up your given P and compare the T given. So if you look up P and then you compare your saturated temperature, you should follow these rules. If you look up your T and you're comparing your P values, you should use this right here. And then if you're given P or T, and then one of these guys, ignore that one, and you're given one of those guys, you'll use this. You can prove it by drawing your PV diagram and see if it's true, but this has worked for me so far. So take a note of that, take pictures, or write it on your textbook or your calculator, because this is a faster way without having to draw it. But that's it for me today. Thank you so much for watching. I hope that these 5 examples help you out, and good luck with your studies.